Hello, today I would like to tell you about our recent paper published in Nature Physics, which reports the discovery of superconducting state with broken time reversal symmetry. In everyday life, we often use the concept of symmetry in relation to the geometrical shape of the objects. For example, flowers, as shown here in this figure, also have a rotational symmetry and mirror reflection symmetry. Time reversal symmetry is a bit more complicated because it involves motion of particles. And in classical mechanics, the violation of time reversal symmetry occurs when the particles do not follow the same path upon their upon their velocity inversion. The well-known example is the cyclotron motion of electrons in magnetic field, shown here. The interesting question is that if it is possible to break time reversal symmetry without external magnetic field, when all physical laws and interactions between particles are time reversal invariant in the beginning. This can happen in many body systems, for example, superconductors, in the result of the spontaneous symmetry breaking. It occurs that such spontaneous symmetry breaking of discrete time reversal symmetry can be engineered for superconductors with complicated band structure. It should have at least 3 superconducting bands, as shown schematically in this plot, where the Cooper pairing occurs. The motion which relates to the time reversal symmetry breaking is tunneling of Cooper pairs between different superconducting bands, which is shown here by the pulsation of Cooper pairs in this animated plot. The most non-trivial property of this motion is that it occurs entirely in momentum space, and there is no motion in the real space. Our task as theoreticians was to show how to translate this momentum space motion of Cooper pairs into the real space. Together with my student in this physical review B paper, we have found theoretically that it is possible if there is an impurity or inhomogeneity in the superconductor. In this case, the orbital and the momentum space motion of Cooper pairs is coupled, and in result there appear superconducting currents, which generate this spontaneous magnetic field with the peculiar structure shown in this figure, which examples spontaneous magnetic field near the spherical inhomogeneity in 3-band superconductor. This magnetic field has a peculiar structure because it is polarized in the AB crystal plane of the material with the C-axis anisotropy. And by now we are quite happy that this fascinating picture agrees with experiments. Experiments was done by the international research team led by experimentalists from Technical University of Dresden. What was measured is the muon spin relaxation rate, the relaxation rate of the spin of muons implanted inside the superconducting material with some complicated chemical formula. The plot here is the main result of the paper, main experimental result, which shows muon spin relaxation rate for 2 different polarizations of the muon beam. Blue plots correspond to the polarization along the C-axis. Actually, such muons feel the presence of the spontaneous magnetic field in the AB plane. And the black dots show the depolarization rate for muons polarized in the AB plane. The difference between spin relaxation rates here shows the presence of magnetic field, which are polarized exactly in the AB plane in accordance with the theoretical prediction. The mechanism that we have found can help to understand the nature of the superconducting state in other exotic materials, which also feature spontaneous magnetic fields below the critical temperature. This is very important for the future development of quantum technologies, since, as you will probably have heard, exotic superconductors can be the main building blocks of topologically protected quantum computers. Thanks a lot for the attention.